second law a little closer, F equals ma, and learn how to do a little bit of the math. So here's your equation, Fnet equals ma. So we're going to start by looking at what Fnet is, and then we'll get into some different equations where we tie Fnet to acceleration and acceleration back to the 1D motion equations. So Fnet equals net force, m equals mass, a equals acceleration, and all of Newton's laws relate, or these laws that we're talking about, laws of motion, relate force to motion. So what is a force? Force can be either a push or a pull. Both of them would be forces. And then we're going to use these things called force diagrams, where before we do a problem, we might draw a picture of all the different forces going on. And after we do that, then we might do some math with it. So just some forces that you'll often see. Force applied is just a common way of saying push or pull that someone's doing. Force friction is going to be a force that opposes any sort of motion. We'll learn about that in a different unit. Weight is the object pushing down, because the Earth is pulling the object down, so that would be weight. And then normal force is the force of the ground actually pushing back up. So when we do a force diagram, let's just talk about the force diagram a bit more. We can draw a quick picture, but we always draw these forces from the center. So whether it's push or pull, they'll be from the center. So friction's going back this way. This person's putting a force forward, and what this does is you can tell the object it's centered on the object that's going to interact with those forces and possibly accelerate if there's a net force that's not zero. Free body diagram is pretty much the same thing as you saw here, but you just take out you draw a dot instead of all of the object. You don't have to be a good artist to do a free body diagram, and that's all you do. Okay, and then this goes a little bit into weight and normal force. If you take a look, weight wants an object to accelerate down. That's that 10 meters per second squared. That's a result of the force of gravity accelerating an object. But if an object's sitting on a surface, you have this thing called normal force, which is just the pushing back equal to the object's weight on a horizontal surface, which you see right here. And without it, take a look at how the box accelerates. It starts speeding up until it hits the ground, and then there's a normal force again, slowing it down. So it's any surface pushing back against an object's weight, and we're going to depict that by just F capital N. Don't confuse that with net force, which I'll do F, and then just a little like this would be net force. Whereas if I'm talking about normal force, it's just going to be F capital N. Okay, so let's look at net force a little bit more. When you have one force, then that is your net force. But when you have more than one force, you're going to have an overall force. And you can see I kind of drew the vector arrows to represent how much force would actually come from these. And we're going to look at each of these scenarios and solve through a couple problems. So what's the magnitude of net force when a person pushes a box with 1 Newton of force to the west? Well, it's going to be exactly that. It would be 1 Newton. And since I said magnitude, I didn't want west. But if I didn't say magnitude, I would have wanted 1 Newton west as the net force. Okay, and here you have two people pushing to the west, each with 1 Newton. So I made all these examples right now, 1 Newton each. And so this would be 2 Newtons. 2 Newtons to the west, but the magnitude itself would be just 2 Newtons. And now you have 2 people pushing opposite directions. Well, you're going to have no net force in this case. So it'd just be +1 -1. And then you can start doing problems at an angle. So here you have 2 people pushing at an angle, so you have to kind of come up with overall. You want to draw the forces head to tail, not draw them like you see here. So you have an actual triangle that has a resultant in the right direction, which would be that. And then to get magnitude, since it says magnitude, you just have to go ahead and figure out what this hypotenuse is. And so doing SOHCAHTOA, 1 squared plus 1 squared, take square root of that, and you get 1.41 newtons. So this right here would be 1.41 newtons as your answer. Once again, magnitude. If I didn't ask you for magnitude, I would have expected you to give me the angle and everything else, which I'll do in the next problem. Okay, so this is the next problem. We have 3 forces going on, and we're trying to figure out the net force. We got this one guy pushing up, this other guy pushing left, and the other guy pushing in, down to the right. And so we're trying to find where the net force is so we can figure out where our acceleration is going to be. And so we're going to have to take this vector that has the x and y component, we're going to have to break it up. This one is only an x, this one's only a y. And so we're going to do SOHCAHTOA to break it up. So if you take a look, we can find the opposite and adjacent side. When we found the adjacent side, that'd be our x, and when we find the opposite side, that'd be our y. So let's find our adjacent side. Let's figure out what we're going to add to this one, what's going to go with that one. So we're finding a component of this arrow right here. And so it's going to be cosine of 30 times the than the 1, because it was 1 Newton of force, and you get 0.866 newtons. So this is going to be 0.866 newtons, and now we want to go ahead and we want to figure out what this opposite side that's going to be a y value. And so sine, because it's straight across, it opens up to the sine. It's going to be sine of the 30 times the 1, and you get 0.5. And so we put the 0.5 newtons in here, and then we see that triangle drawn again right here. So now we have our components. We're no longer concerned with this part, so we're going to go ahead and get rid of that. We want to go ahead and we want to figure out a total x, so we want to get this and this and put those together. So to get total x, we're going to say 1 west and 0.866 east. We have to go ahead and use direction signs, so we'll say west is negative. Add those together and you get an overall negative answer, which ends up being 0.134 newtons west. Now we can go ahead and figure out what our total y is. So we're going to go ahead and take this and we're going to put that together with this. So we 1 north and 0.5 south. We're going to call the north positive and south negative. And we get an overall positive, which would be 0.5 north. Now we're going to go ahead and I'll just do my x first. We're going to go ahead and draw an origin dot. We'll do this one first. We'll do that one second. We end up drawing this triangle right here. And we will put our components, because these are components, on the triangle. And we have to solve for the overall. We're going to find the C, the hypotenuse right here. And to do that, we'll take our sides, take the square root of each of our sides squared. So square root of 0.5 squared plus 0.134 squared, both of those underneath the square root, and we get 0.518. So this C is 0.518. And now we can go ahead and figure out this angle by taking the inverse tangent. So we need to know our opposite and adjacent. So opposite, it opens up to this opposite. Adjacent's over here on the side. Plug in our values. And when you type it in, double check, make sure your calculator's in degrees, but mode's in degrees, or else if you're in radians, you're not going to see this answer, but you get 75. You get 75 degrees as your answer here. And now we're ready to come up with a final answer, and this would be 0.518 newtons, 75 degrees. In this case, it's going to be of west right here. Last thing you see is going to be west, so it's going to be north of the west. So that's your complete final answer. If I didn't say magnitude and I gave you a problem like this, it takes a little bit of time, but that's what I would expect. When anytime I say magnitude, I'm just looking for the C. Okay, so what's net force? Looking at this picture, often we have forces of nature. Anything sitting on a counter, not accelerating, is going to have balanced forces. So you have those two forces balancing each other off. But then these left and rights don't balance each other off. And you can go ahead and you can see when the x-axis, you can call this negative, call that one positive, add them together, and you end up getting a negative 40 right here, which could be drawn in. So this here, this itself, is going to be the net force. So this would be the overall force as a result of all these other forces going on. Okay, so this one, once again, is the net force. Okay, so let's go ahead and let's do some problems where we solve for A or F or M, and then we'll do some problems where we take the we tie this to 1D motion and look at our acceleration problem, because this has an acceleration in it, so this is going to tie to some other equations. Just a reminder of the variables we're going to use here. Force is going to be a Newton, a capital N. Mass is going to be, or M is going to be kilograms. A is going to be acceleration. VI is going to be initial velocity. So acceleration, back to acceleration, is meters per second squared. So things to look for as you're trying to decide what you're given. The units are going to help you figure out what you're given. We're going to deal with velocities, initial and final. This is not going to be constant. It's not going to have V, because acceleration makes the velocity change. So we'll have VIs and VFs. We'll have displacement as X in our equations, and then we'll have time as T, which would be in seconds. So displacement, the unit is meters, and all the velocities are meters per second. Okay, so that brings us back. Once we can solve for A, it's going to bring us back to these equations. So this is pretty much the main slide. You're going to stop at one slide and just stare at it for a little bit. This is the one to stare at. We're either going to be given F and M, and we're going to solve for A, and then after we solve for A, we're going to look for a 1D motion equation, or we're going to be given enough information to use that to solve for A, and then we'll be asked something over here. So we're going to kind of go back and forth, just a two-step. You decide, do you have enough information here to solve for A, and then can you use that for some other questions? So that's what we'll do here. But before we get into any of the difficult ones, let's just look at the F equals MA. And I'm just going to give you one force, so this would be our net force. What's the force required to accelerate a 10 kilogram object by 3 meters per second? So F equals question mark, M equals 10 kilograms, A equals 3 meters per second, and then you just go to the equation, plug in your variables, and you get 30 newtons. Next problem, what's the force required to accelerate a 50 kilogram object? So same sort of setup, now we have 50 kilograms, we have an acceleration of 3, and it's going to require a whole lot more force, and the reason why I asked you this is it requires a whole lot more force, 150 newtons, because you have a bigger object, and that leads you to the next question. It's going to have much more inertia. So the 50 kilogram object is going to have more inertia, which therefore would require more force to get the same amount of acceleration from it. So now we're ready for our two-step problems. We have to figure out what information we have and where we have to go from here. So we're going to make a big old givens list, and we're going to decide, do we start with F equals ma, or do we start with these other equations? And usually it will somewhat, not completely obvious, but it'll be somewhat obvious because of what the question's asking you for, where to start. So here, a constant forward net force of 1,000 newtons is applied to a car with a total mass of 1,500 kilograms. So there's their F and their M. How much faster? So it's asking you for VF. Will a motorcycle be traveling after 4 seconds? So let me just get all my givens list. So you got after 4 seconds, starting from rest, a mass of 1,500. They tell you the force that's going to be applied. They ask you how fast you're going, and what you have to realize is that you just don't. You have only 2 of these equations known and one unknown. You need more information. Pretty much, if you have F and M, you're going to start by solving for A, that's what you do here. So where you can use the F equals ma equation, and we're going to solve for acceleration, and then we'll have acceleration. Once we have this, then we can go ahead and pick one of these 1D motion equations, acceleration equations. So we have A equals F over M, and our F is 1,000, our mass is 1,500. We get a 0.667 meters per second acceleration. So now that we have 0.667 meters per second, we have A, we have VF, we have VI, and we have T, and that's going to lead you to this one equation, the only one that has those 4 variables. So this is pretty much the steps, and now you should remember this from a previous lesson. It's just kind of following along, plugging in the variables, plugging in the numbers, and you'd get 2.67 meters per second as your answer here. Okay, 11. How much force is required to brake by the brakes to stop a 1,000 kilogram car from moving at 30 meters per second in 5 seconds? So let's start looking at our givens. How much force is the question? We're trying to get to a stop, so our final velocity is 0. Our mass is 1,000 kilograms. Our initial velocity was 30. It's going to take us 5 seconds to stop. And now we're going to need acceleration because we're trying to find force. We have mass right here. So if we can find we know acceleration, and we can figure this one out, then we have the M and A to do the F equals ma equation. So we're going to go ahead and let's go ahead and let's figure out our acceleration. We're going to use the variables we have here. We have three knowns out of, once again, we're going into these questions, 3 knowns and 1 unknown, and you'll see there's one equation you can go to. Once again, same one as before. It's not always going to be the same equation, so you always have to watch out. You can use one of these equations based on the givens that you were given in the problem. So we plug in our values. We have to subtract the 30 from both sides to get rid of the 30. We can't take the 5 and 30 and put them together. This is 5a's. We need to subtract the 30. So we subtract 30, that gets rid of that. And we get negative 30 equals A times 5, and now we have A equals negative 30 over 5. And you get a negative 6 meters per second squared, so you have a force opposing this object. And you should expect a negative because you're stopping an object, so you'd expect a reverse acceleration to go on. And now we have acceleration. Now we have the A as well, and we have the mass, and we can go and plug this in. So there's your 1,000 newtons, and there's your negative 6 meters per second squared. And we get a negative 6,000 Newton force. So that's how much how much force would be required to stop this car. Next problem, what's the final velocity of a 1,200 kilogram car starting from rest after 50 meters when 4,500 newtons of force is applied? So these are the givens. It's asking you for final velocity. They give you the mass 1,200 kilograms. They give you initial velocity. It's going to start from rest. We're going 50 meters. We're allowed to go 50 meters. And they tell you a force of 4,500 newtons. And we're going to need, so what we're looking right now, we have VF, we have VI. We're asked for, and they're going to ask you for the final velocity. So we have X. If we can find A, then we can solve for VF. So we need to go ahead and we have to use our mass and our force to solve for A. So F equals ma. We rearrange that, so you divide out the mass, you get A equals F over M, or same thing as A equals F over M. We plug in our values, 4,500 to 1,200, once again looking at what we have and where we can start. And we plug it in, we get 3.75. So now that we have our acceleration, now we have a VF, a VI, a X, and an A, and we can pick our best equation, and that's going to lead you to this equation, VF, VI, A, and X. Pretty much every time you are given mass and force, expect to start with A. And if you're given other things, you're probably going to have to start in another with the 1D motion equation. So here we'll plug in our values. We'll take the square root of both sides. That gets rid of this df squared. And so we plug in our values. Make sure everything is underneath the parentheses. So I was actually missing a parentheses here. Everything should be underneath the square root. And when you plug in your value and you get your answer, type it in the calculator, you should get 19.36 meters per second as our answer. Okay, so this question, all I do is, it's the only step further I give you is I give you two forces. You have to figure out the net force, and then once you find the net force, then you're going to do the problem. So you have a 10 kilogram box. How is going to be moving from rest after 3 seconds. I have a 200 Newton force applied to the left and 50 Newton force applied to the right, just what you see in this picture. And so we can find our overall. We make the left negative, right positive. We get negative 150 or just 150 newtons to the left, and then we can start doing the problem. It's asking you for how fast it's moving at the end. So final, it's telling you its mass. It tells you it started at 0 meters per second. It tells you 3 seconds it took. And we have our force from up here. This will be our Fnet. But we can really use this acceleration, and we have F and we have M. So we're going to start with the F equals ma equation. And we rearrange that, plug it in. And so A equals F over M. A equals F over M, and then so A 150 over 10, we get 15 meters per second squared. And now we can go ahead and pick our equation that has the other givens. VF we're solving for. We have a VI, we have a T, we have an A, and that's going to lead you to this equation. Plugging in your values, you're going to get a final velocity of 45 meters per second. Okay, and then the last problem. So this one, I just give you one force, but now I'm giving it to you at an angle. The only force that's going to go, into the acceleration is the force in the direction of the motion. So for a problem like this, we actually have to figure out what is the horizontal force, because the force that she's applying is at a 25-degree angle. So if we can go ahead and break that down and find the horizontal component, this is the only component that's going to go into the motion, since this wagon's on the ground. So we need to find the Fx, the horizontal force, when we're given this angled force. So there's going to be some wasted force right here. We'll see in friction this is going to be important, but for now it's just wasted. It's not going to go into anything. So we find this side, which is the adjacent side. We have our hypotenuse. Plug in our values. So there's cosine of 25 times 200. Once again, make sure you're in degrees, not radians. And we get 181.26. So this is 181.26 newtons. This is the only force that's going to go into acceleration. So just one step further than the kind of problems we were just doing 2 problems ago. So we have our net force. We have a mass from the problem. We have initial 0 meters per second. We know it happens in 3 seconds. We're solving for VF. We have M and F, so we can go ahead and solve for A that way. Go ahead and solve for A. Once again, M or A equals F over M when you rearrange that equation. So we get F over M, we plug in our values, and we get 403 meters per second. Now we can use our givens that we have here, the VF, VI, T, and A. And we pick this equation because this is the one that has all those variables. And we can plug in the variables, and we finally get an answer of 12.9 meters per second.